Okay, and finally, let's look at an example of a synthesis. If I asked you to synthesize this target molecule, and I gave you a hint, I said you should start with some kind of epoxide and some kind of nucleophile. That will help you maybe see the pattern in the target molecule that makes it look like a product that might have come from an epoxide ring opening. So what do those ring opening products look like? Well, they always have an OH on one carbon, and the next carbon over, we have a nucleophile that's been added. Okay, now it is possible to add a methyl and an ethyl via a Grignard reagent, but this oxygen group most definitely, he couldn't have been there in the epoxide form. So this was my nucleophile. This was the group that was added, so that's kind of the disconnection that we're making here. If you want to imagine doing in your retrosynthesis, right, we're asking what starting materials do I need. You can almost imagine doing that backwards reaction where the epoxide ring closes back up and kicks the leaving group out. So instead of just doing a disconnection, you could think about that reverse mechanism, that imaginary reverse mechanism. The stereochemistry on this carbon stays the same. I still have a methyl back and a hydrogen out. Okay, but I want you to think carefully about the stereochemistry of this. What did the stereochemistry used to be over here? We have a wedge and a dash, so we need to fill in. What did these groups used to look like so that after the nucleophile added in, we ended up with this stereochemistry at the carbon? Okay, now think about what it means to be an SN2 and do an inversion of stereochemistry. I want to point this out because when our leaving group is in the plane, it's a little different than some of the examples we've seen. Just by having this oxygen come in from in the plane, it causes the dash and wedge bonds to be pointing out in the up direction, and then the inversion now points them in the down direction. Okay, so because my ethyl group was a wedge and my methyl group was a dash, there's still going to be a wedge and a dash when this nucleophile adds in. Okay? My nucleophile, because my leaving group in this case, let's think about it in the forward direction. My nucleophile in this case is in the plane. I'm sorry, my leaving group is in the plane. That means my nucleophile must come in from in the plane. Approach from in the plane. It's not going to come in as a wedge or a dash because my leaving group is a straight line. So that means the nucleophile comes in, ends up as a straight line. So the inversion, you have already seen the 180 degrees. It used to be up here, and now it's down here. There's your inversion. And the other two groups are simply like your umbrella flip. The one group that was pointing out towards you is still pointing out towards you. But instead of going down, it's going up a little bit. There's no way for these groups to do this. That would be, again, a double inversion. You can check your stereochemistries here. If you want to assign RNS before and assign RNS afterwards, you will be able to confirm that they've indeed inverted if you're not convinced by this or if you're having some trouble with this. Okay, of course, working with a model can help as well. Okay, so this is my epoxide. That's my electrophile. So I know I need a nucleophile. Who is my nucleophile? Needs to be this ethoxy group. So maybe I can have sodium ethoxide. That would certainly be a nucleophile. And this might be a good way to do this synthesis. Okay, but what we need to do after we do our planning is we need to check to make sure that would work. Now, if I took these two, this epoxide and ethoxide, and I went to predict the product, would this give the target molecule? Well, how do we decide that? We take a look at our reaction, we think about the regiochemistry, we think about the stereochemistry, or we need to confirm it as if it were a predict the product. So do we have acid catalyzed conditions or base catalyzed conditions here? Clearly this is a strong base, so there's no acid here, which means the ethoxy group would go where? It would go to the less sterically hindered carbon. So what product would I get? I would get the product where my ethoxy group adds to the carbon on the left, and the alcohol would end up on the carbon on the right. Now let's think about that stereochemistry here. My ethoxy group would come in from down here, so that kicked off the oxygen. What happens to this methyl and this hydrogen? The hydrogen is still a wedge, but it's up here a little bit. The methyl is still a dash, but it's up here a little bit. Okay, this would be the product formed by this synthesis. Is that the product we want? No, that's the wrong regiochemistry. I don't want the OH on this tertiary carbon. I want the OH over here on the secondary carbon. Okay, so this is not going to work. This gives the wrong product. It gives the wrong regiochemistry. So how do I force my nucleophile into this carbon? I want the nucleophile to attack this carbon. How do we force it over there? How do we get the nucleophile to go to the more substituted carbon? We do it by using a strong acid so that it will be the protonated epoxide that gets attacked. So how do I do that? I don't use methoxide, I use methanol. I'm sorry, I don't use ethoxide, I use ethanol and a strong acid. I can't, H2SO4. I can't use ethoxide anymore. What would happen to ethoxide if I tried to mix that with acid? It would simply get protonated. So remember, it's okay to have a weak nucleophile. We need to have a weak nucleophile when we're in acidic conditions. It's impossible to have a strong nucleophile in acidic conditions. Okay, so I would use ethanol, NH2SO4, and now when I go to predict the product, I protonate the oxygen and my ethanol goes to the more substituted carbon and I get this target molecule out instead. Now this is an interesting thing to point out. I have a tertiary carbon here. I'm doing an SN2 on a tertiary carbon. This is the first time we've ever seen that, and this is the only time we're ever going to see that. What's unique about this mechanism is that it's not an ordinary SN2. We've always said SN2s don't happen on tertiary carbons. What's different about this mechanism? Because of the strong acid, because we're protonating the oxygen, it now is an SN2 with some SN1 character, right? So it's that SN1 character, it's that presence of that positive charge that makes it different from an ordinary SN2. And now we go to the more substituted carbon, even if it's tertiary, and we do our backside attack. Okay, so we saw lots of examples here about ethers, how to synthesize ethers, what reactions do ethers undergo, what are some physical properties. Of course, the most interesting ether that we have is the epoxide. So we saw lots of examples of epoxide ring opening reactions and stereochemistry, regiochemistry implications of those. Hope to see you next time on Educator.com. Thank you.